Hello everyone, I'm Dr. G and welcome to today's lesson on the hydrogen atom. Specifically, we're going to be talking about the quantum mechanics of the hydrogen atom. And this video is nearly 2 hours long, so I don't expect too many people to want to watch it straight through, right? I imagine most people, the best way to learn this is in chunks, right? So watch from maybe timestamp to timestamp, because I'm going to put timestamps in the video description to make that easy to do so that you can break this up into smaller bits. This is also the type of material that very few people will understand with one pass, right? The first time they hear it, they get it. That's almost no one, right? Almost everyone needs to hear this sort of material more than once. So you may rewatch certain sections again and again until it finally clicks for you. Another thing that I suggest you do is frequently pause the video and, stare at the equations that I'm talking about to make sure that they make sense to you. You want to make sure that you actually believe them, right? Maybe you understand the algebraic step going from the previous step to the current equation. Or perhaps, I talk about how, this equation is similar to another one, plus there's this other little correction in here. And then I want you to go ahead and, look up that other equation, compare them. See if you believe it for yourself that yes, these really do look similar and I believe what you're saying, right? So I want you to make sure that you really take the time to internalize the equations, to understand them for yourself, to believe them for yourself. And again, this is probably going to take you multiple passes over many sections of this. So I actually recommend, if you're watching this video on a device with a keyboard, I suggest you watch it with your right hand in the home position on your keyboard, right? So your index finger, J, K, L, right? These three fingers, J, K, and L. And the K button on YouTube will pause and play. So if you need to pause it, just hit it with your middle finger. And then play it again if you feel that you have it, right? And so J will back up 10 seconds and L will go forwards 10 seconds. So if you keep your hand resting there, you can pause it, back up 10 seconds, move forward 10 seconds. You can do this all very quickly with a single keystroke. And I think that'll be a much more efficient way to watch this video because if you need to hear something again, just hit that J button and back it up 10 seconds and hear it again, or hit it twice and then they'll get you 20 seconds, etc. So all this being said, I really hope you enjoy the video, and I hope that it gives you a good appreciation for all that went into finding a quantum mechanical description of the hydrogen atom. All right, everybody, enjoy. Hello, everyone. Dr. G here, and we're going to be talking about the hydrogen atom today, and specifically, we're going to be talking about a quantum mechanical description of a hydrogen atom. And honestly, with something as small as a hydrogen atom, if you're not using quantum mechanics to describe it, you're not saying all that much. So that's what we're going to be doing today. We're going to be solving the Schrödinger equation for a hydrogen atom. And first I want to make note that I'm going to be drawing heavily from a really great textbook called Physical Chemistry, How Chemistry Works by Professor Kurt Koloshinsky. He's a great professor, and this is a great book. So you might notice some of the equations have numbers on them, and the equations are numbered as they are in that particular book. But of course, the physics of the hydrogen atom, the quantum mechanical description of the hydrogen atom, is general to anyone studying this particular topic, regardless of which book you are using. All right, so let's get into it. So we're going to begin with the Bohr atom. Now, the Bohr atom was actually not quite correct, but it was a really important step in describing the physics of the hydrogen atom. And basically, it began with an experimental observation. So Balmer-Rydberg-Ritz, that's the formula at the bottom there. And basically, that was based on observation of the emission spectrum of hydrogen. And this was actually first measured by angstrom, right? So the unit of distance, angstrom, right? That's how you know you've made it, seriously made it, right? If you have a unit named after you, that's about as good as it gets. So so this measurement was first made by angstrom. And so here we have an image, and we see there's very sharply defined peaks, where basically you're going to see certain wave numbers of light very strongly and some not at all. And at the time, this was very puzzling to people. They weren't sure why this was the case. And so basically the idea was like, well, maybe we can come up with a mathematical function that at least empirically fits that, right? So maybe there wasn't any theory to describe why the math the way it is, but hey, at least you've got something so that the math matches the observation. And so that's what we see here with the Balmer-Rydberg-Ritz formula, right? So those three found a mathematical form that fits this data. Now, and that form is shown down below there. And importantly, they did not have a justification for it, really. So they said, all right, we have these two numbers, n1 and n2. And notice that there's some constraints on them. n1 must be smaller than n2, and they must be integers, right? You can't have n1 equals 1.1 or something like that, right? It has to be integers. So, this gave some information. And then, of course, that constant there, that r sub h, that is a scaling constant. So basically, this functional form here, this 1 over n1 squared minus 1 over n2 squared, that functional form will give you the correct relative spacing. But for it to fit overall, you have to multiply it by some scaling constant. And that turned out to be that 109,667.581 there of wave number, right? 1 over centimeters. That's wave number. So so that's what we see here. That basically, if you multiply by that number, so they basically found what the scaling constant was, then these things will line up perfectly. And that's great. It's an observation. It's an empirical way of fitting a mathematical form that fits the data really well. And that's a huge discovery, right? That's worth a very good research paper right there if you discover something like that. But it's not a complete description, right? We want to try and do even better. And so we're going to keep going with this as the scientific community did. And, I think it's important to note here that the fact that there's integers involved, right? At the time, they didn't have explanation. Why do these have to be integers? I don't know. They just do, right? It fits the data. But another way of saying that things can only be integers, right? That there's some, I always kind of think of it as like if you have like a knob that you turn and it's continuous, then that's not an integer, right? That's more like a decimal, right? Or a real number, sometimes we call that, right? So that'd be like if it continuously change, but that's not the case here. It can only be an integer. So then I think of that as like a knob that kind of clicks into place, right? Where you can be at either 0, 1, 2, 3, 4, right? But there's no 1.5, there's no 2 3/4, right? Nothing like that. There's just integers. So another way to describe that is to say that it's quantized. So basically this was one of the first times, if not the first time, in the scientific literature that a quantization came up. And at the time, they couldn't explain why, but it seemed important, and it sure is important. It's extremely important. That's sort of the biggest thing here, is that they noticed that there's a quantization. And so, of course, quantum mechanics, that's why we call it quantum mechanics. Mechanics of things that are quantized, something that can be at either the lowest energy level or one level up and nothing in between, right? Or one level up from that, but nothing in between, right? It's quantization. So that's a really important thing that came out of this, is quantization. So the Balmer-Rydberg-Ritz relationship we just talked about, had that quantization in it, right? Said, there's for some reason things are quantized. Not sure what that even means, right? So then Bohr made a really great first guess at trying to figure this out, and it ended up being not quite right, but it was such a good guess, it was worth a Nobel Prize, well deserved. So Bohr rationalized this, right? He thought, okay, just as the moon can remain in orbit around the Earth due to its centrifugal force being in imperfect balance with the gravitational force experienced by the moon, perhaps electrons also orbit the nucleus along only certain allowed radial distances. So this was sort of the thinking, right? These are, not exact, wasn't a quote or anything, but this is roughly what the thinking was, is maybe we can relate these two to each other. Orbital motion, can we relate that to this idea of this quantization, and thinking like, okay, well, maybe a higher energy level, you can be one or the other, right? You could be 1, 2, or 3 for this n value here, nothing in between, and those correspond to different size orbits. And it ended up being not quite right, but it was definitely a step very much in the right direction. And so let's go over some of the math behind that now. So we note there's the equation at the top left, that gm over r squared one, right? So that equation is relating this balance between these forces, right? Just as we see the idea of the centrifugal force as being perfectly balanced with the centripetal force, right? So that's sort of idea of how the moon stays in orbit, right? The moon doesn't fall to Earth. at least not anytime soon, right? So, so we've got gm over r squared. So gravity is a gravitational constant. M is the mass. So basically, like if the one mass is a lot bigger than the other one, you just kind of add them together. But anyway, that's a mass value, and it's over r squared. R is a distance, and then r is on the other side as well, and v is a velocity. So the velocity of the orbiting body. And then we look at what Bohr did here, and it's very, very similar if we pay attention to the functional form, right? That E squared, that's sort of, that's the charge on one electron. That has to do with, that you can think of that as being similar to G in this case. And basically that E naught is, we call that the permittivity of a vacuum. For now, just think of it, that's a constant as well. And 4 pi, of course, that's a constant as well. So you've got some constant with some constant multiplied by a 1 over r squared on the left side. Same as the orbital thing at the top left, right? It's the same sort of idea, right? We've got some constant multiplied by 1 over r squared. And on the right side, we've got basically velocity squared over r again. And we've got a constant over here too. But, not paying too much attention to the constants, we see that this is the same principle here, right? We have this balance between the Coulombic force, right? The Coulombic force is the attraction here, right? So like the attraction of the negative electron to the positive nucleus, right? That's the Coulombic force. And then centripetal force, right? Centripetal force is basically, if you've ever gone on one of those rides that spins around real fast, like the gravitron, right? That force that's pushing you outward, that is the centripetal force, right? So that's basically what's going on, is that you've got an attractive force that's pulling you towards the center, right? Which is more similar. But and again, he's thinking of an electron orbiting the nucleus. That turned out to be not quite right. But nonetheless, that's the thought process here. That's the logical path we're following at the moment. So on one hand, the electron's being attracted to the nucleus, but then that force is being balanced out by another force that's effectively pushing it away from the nucleus, which we call the centripetal force. And that's, and this is the idea with the moon, right? The centripetal force pushes it away, and the gravitational force pulls it towards, and they stay in perfect balance, and the moon just keeps going around the Earth. So Bohr thought, hey, why not the electron and the proton of a hydrogen atom? Maybe it's the same kind of deal here, and they're in perfect balance. So that's what we have on the left side. We have the attractive component, and on the right side we have the centripetal force that's pushing it away. So of course on the left side it's really only dependent on the distance. Right, that makes sense. The further you get away from the Earth, the weaker gravity gets, right, or anything like that. Same thing with the electric charges. And then on the right side, it is a function of both the distance r and also how fast you're going. Right, the faster you go, the more the attractive force is getting weakened by the centripetal force. Okay, so again, we have this balance of Coulombic force pulling the electron towards the nucleus on the left side of the equation, and the centripetal force pushing it away due to the path that it's taking on the right side of the equation. And now we have to think about, okay, what's up with the integers? Okay, so maybe there's this balance of forces here, but then how do we involve the integers? So then Bohr proposed, what if we think that the angular momentum, let's define the angular momentum this way, so that m sub e is the mass of an electron, u is the velocity again, h is Planck's constant over 2 pi, and if there's just an h, it's not over 2 pi, it's just the constant, but we divide it by 2 pi so often that, we do h bar. So this is Planck's constant over 2 pi, and n is some positive integer. So that's what we've got now. And so basically, what this equation is telling us is that the angular momentum has to be some integer multiple of Planck's constant. So it's almost, it's basically saying, like, what if the angular momentum is quantized? You can only have certain values of angular momentum, and it's going to be some multiple of Planck's constant. So the smallest one we have is 1 times Planck's constant, or 2 is the next smallest, right? And so on. So it's quantized. He's saying, what if angular momentum has to be quantized? So it turns out that these expressions can actually be combined in such a way that you can derive the mean radius of the orbit of an electron in the ground state of hydrogen, which is pretty wild. So again, as I mentioned, Bohr wasn't quite right, but boy, was he, compared to where we were before, this was a tremendous step in the right direction. And in fact, at least as far as the mean goes, the mean radius, it can predict to a pretty good degree of accuracy here. So that's pretty amazing. So let's go ahead and give that a shot here. So, we have the two equations on the left and the right. And the first step, let's get the velocity squared by itself on the left side here. So all we did was, divide both sides by m sub v and multiply both sides by r on the left here. And then on the right, let's get velocity by itself as well. And you know what, let's square it so that they match. So basically we do a little more algebra. We bring the m sub v and the r over to the right side, and then we square both sides. And we have those values there. So now we have two expressions that are both equal to velocity squared. Well, then that must mean they're equal to each other. So let's put them together. We've got this expression right here. That's all we did at this point. We just put the two together. And from this point, we can make a definition here, right? So notice there's a ton of constants here, right? 4 pi e naught, h bar squared, m sub v, e squared. Those are all constants. So what if we just combine those into a constant we'll call a naught? And if we do that, then basically our formula becomes much simpler to look at, right? It's n squared times a naught. And it turns out that if we go for the ground state, right, the lowest possible energy state, we call that the ground state. That's n equals 1. So if you set n equals 1, then a naught equals this value right here, which is picometers. That's in picometers. That's the unit, right? And as we mentioned, what do we say this predicts? The mean radius of the orbit of an electron in the ground state of hydrogen, right? So if the electron is really orbiting the nucleus, this would be the the mean radius. And it turns out this, if you were to measure that distance, this is about it, right? So this is an amazing prediction. Again, the theory's a little off, but it was so close that especially compared to where we were before, right? You always have to say compared to what? Anytime you say something's good compared to what? Well, look where we were before. We were just putting integers and we didn't know why, right? So this was a huge step. So this is known as 1 Bohr radius. So this is a famous unit of measure. There are computational chemistry software packages that are being made to this day that use this as the unit of distance. A Bohr radius is sort of one of the, that's one way of measuring distance, right? What's a meter? What's a foot, right? Somebody has to establish what a standard distance is going to be. This is a great standard to make. And so you still see the Bohr radius as a unit of measure often used all over the place, but I've seen it in computational chemistry software packages. So, the Bohr atom, great first guess, but, what do you think the problems might be with this? So taking a moment to think about that, maybe even pause the video, go back, back it up a little bit, take a look at the equation and see what you think. See if you can kind of come up with any reasons why maybe this isn't so perfect, right? And so now let's take a look at some of them. So one, there's no explanation for the quantization here. So, that was the problem with that first equation where they fit it to the observed spectrum, is that they said, well, okay, you got the n1 has to be less than n2 and have to be integers. No one knows why. And again, Bohr did a similar thing, because remember there was a step where we said like, well, what if the angular momentum has to be quantized? He was right about it, but like, he just said, I don't know, I guess it has to be, right? I don't know. So, that's what we call ad hoc to this. We say, okay, this is the way it has to be. Don't ask me why, right? So we didn't explain it. We can do better, right? So Bohr did an amazing Nobel Prize winning thing, but can we do better? Yes, we can. Here's another thing too, is that this idea of forbidden and allowed radii for the orbit, right? If the electron is allowed to orbit at some distances but not others, we know that it changes from one to another, right? Because that's why we see emission spectrum, right? When the electron goes from a higher energy state to a lower one, that energy, energy is never created or destroyed, so it gets released as light, and that's the spectrum we see. Well, okay, when it goes from one to the other, what happens in the middle? If these forbidden things, like it kind of, if it went from, two Bohr radii to one down to one Bohr radii, right? It went to a lower energy level, right? It's closer to the nucleus. Just like if you jump off of something high to something low, you've decreased your gravitational potential energy. Same kind of deal. But if you jump off of something like that, didn't you pass through all sorts of other distances on the way down? Well, yeah, you did. And wouldn't the electron? So that kind of didn't seem to make sense with what Bohr proposed. Another thing. So, at the time, and we're still obviously aware of it, but they were aware of it at this time too, de Broglie wavelengths. This idea that particles traveling don't go in these perfectly straight lines, right? They don't travel like a ball that you throw, right? The adjective we use for that, ballistic, ballistic. It's something like a ball. They don't go like that. We know this, right? They go in like waves. So again, if it's going around the orbit in a wave, isn't it then going nearer and farther from the nucleus as it goes? It'd be kind of going back and forth. Look at that little pink pattern to the bottom right there, right? It would be doing that. So it'd be kind of going in and out of these forbidden distances the entire time. So that it just does not add up. So, all right, so let's take it another step. Let's try and do even better. Okay, so we've talked about quantum mechanics at this point in previous videos, previous lessons. If you have me in class, we've talked about things like a quantum particle in a box, right? And for that, we solved the time-independent Schrödinger equation, which we see here, right? H psi equals E psi, right? The Hamiltonian operator acts on the wave function psi, and the wave function comes out unscathed, just multiplied by a constant E, an eigenvalue, which is an energy. Turns out that's the energy of a particular wave function state. And so what we need to do the same thing here. So remember we had a Hamiltonian. We say, okay, the energy is infinite if it goes through the wall and zero if it's inside of the wall, right? That's the quantum particle in a box, in an infinitely strong box. So, it's all about defining that Hamiltonian so then you can operate with it onto a wave function and basically solve a differential equation. Or in our case, it's going to be a partial differential equation. So there's going to be multiple partial derivatives of a multivariable function. And we're trying to answer the question, what function satisfies this, right? That's the whole point of solving differential equations is conditions, a set of conditions. And then the question is, well, what function or family of functions satisfies this? That's what we're trying to solve. So we need to define our Hamiltonian operator, which is, it's going to be the sum of the kinetic and potential energy, right? That T plus V, that's what that means. And so for a particle here, we're going to say that T is minus h bar squared over 2 mu times that upside down, or that triangle there, that triangle squared, right? That means that's the Laplacian. That's an operator that we call the Laplacian. We're going to define that carefully moving forward. But you could think of it almost, it's not taking a derivative twice, but it's kind of similar to that. And if you think of 1/2 mv squared, right? 1/2 mv squared, what's that? That's the kinetic energy of a classical particle, right? 1/2 the mass times the velocity squared. So that T, the kinetic energy operator here, is equal to minus h bar squared over 2 mu times that operator there, that triangle squared looking thing, right? That is the Laplacian. And you can think of that kind of like the derivative operator multiplied by itself. It's a little different. It's really the gradient operator dotted with itself. And it's slightly different. We'll get into it. We're going to define this very carefully moving forward. But for now, I want you to just get a sense that that term is very similar to 1/2 mv squared, right? What's that? Think about that for a second. 1/2 mv squared. That's the kinetic energy of a classical object, right? If you have some particle traveling, just 1/2 mv squared, 1/2 the mass times the velocity squared. So the velocity, that's if you take the derivative of position with respect to time, that's velocity. So if you so that's kind of like, you're multiplying the derivative of position with respect to time by itself. And then that mu right there, that 1 over mu that's in there, notice that is really, that's a reduced mass, but it's masses, right? And then you've got 1/2 is also there. And then of course we have Planck's constant. So we're multiplying by a constant, Planck's constant squared. But you see how that is a very similar form to 1/2 mv squared, kinetic energy. So, I haven't rigorously explained why that's the kinetic energy operator, but I hope I've given you some intuition to at least make that extremely believable that, yeah, that actually does make sense. And then to right of that, the V operator, right? That's the potential energy operator. So potential energy here is minus E squared over 4 pi E naught times 1 over R. So that is the potential energy. And again, we've seen that before, right? Because Bohr was talking about this, right? So he had that right, that we've got this potential energy of the electron being attracted to the nucleus here. So, and that was the term that, like, for the particle in the box, it was just like that discontinuous function we defined, right? Where we said that it's like we call it like a step function, right? Like the potential energy is 0 inside the box, infinite outside the box, right? So instead of saying that, that's a very coarse kind of like thing to do, and it's actually a really useful approximation to use from time to time. But now we're kind of being more precise with saying, okay, the particle isn't trapped in an infinitely strong box. It's trapped in a finite attractive force by a positively charged nucleus. And for hydrogen in this particular case, it could be just a single proton. All right, so we have the Hamiltonian defined thusly. And of course, as I mentioned, we have the potential energy due to the electron being attracted to the nucleus on the term on the right. And, let's do a quick digression here. So if we compare that term on the right, the potential energy term in the Hamiltonian, to what we have in the Bohr expression here, look at the left side there. We've got E squared over 4 pi E naught R squared. So notice Bohr was 1 over R squared, and our Hamiltonian is 1 over R. So is this a mistake? Should we be worried about this? What's the deal with that? Well, the important thing to note is that the Hamiltonian is potential energy, and the E squared over 4 pi E naught R squared on the left over there, that's not potential energy, that's a force. And this is actually quite general. So it turns out that there is a type of field, we call it a conservative field. And if you're in a conservative field, right, so the potential energy function is not changing as a function of time, well, if you take the negative gradient of the potential energy function, you'll get the force. And so, there's only one variable there, right? Because E squared, 4 pi, E naught in that term, right, those are all constants, so R is the variable. So the only thing we can take a derivative with respect to is R. So if we take a gradient, we'll define this more rigorously moving forward, but if you only have one variable, a gradient is a derivative, right? So if I'm just taking the derivative of that respect to R, it is going to be R squared, right, down there in the denominator, and you'll also see the sign change, which it does. So this is actually okay. And I just wanted to point this out because it comes up a lot, and sometimes it can kind of get glossed over. So I just think it's great to point that out, that this concept where you take the negative gradient of a potential energy function, and that gives you a force function. And so here we see it again. So I just like to draw attention to it because I think it's cool. All right. So, I kind of hinted at it before that this kinetic energy operator, it does make sense, right? And it was a little bit of a hand-waving explanation. So let's get a little more serious with it here. So another way that we can think about this is that there's the momentum operator. So this is in quantum mechanics, we say that the momentum operator P is defined thusly: h bar over I times the gradient operator, right? That's the momentum operator. And this is something that would be, previously defined in a quantum mechanics course, but you can take my word for it for now, but make sure you understand this. And that I is, of course, the square root of -1, right? That's the usual meaning of I. So that's the momentum operator. Okay. And then, of course, we're defining that gradient operator rigorously here, right? Where it's this x hat times ddx plus y hat times ddy plus z hat times ddz. So the x, y, and z with the hat over it, this is what we call a unit vector. So if we're looking at a three-dimensional space where we have vectors, and there's three elements, there's x, y, and z, the unit vector for x would be 1, 0, 0, for y would be 0, 1, 0, and z would be 0, 0, 1, right? These are unit vectors. So we call this. So it's the unit vector multiplied by the partial derivative operator. So if you take the partial derivative of a function with respect to x, that's ddx. So that's what we're seeing here. So this is what this operator is. Where it's sort of, we have these three different operations together, each one multiplied by its respective unit vector. All right, this is the gradient. So, the more common way of learning kinetic energy the first time you learn it is 1/2 mv squared. But another way to look at that is p squared over 2m, right? So the 1/2 stays the way it is, and p is m times v. So if you square m times v, then you got m squared v squared, and if you divide that by an m, then you've got it down to mv squared. So these are equivalent. It's the same old kinetic energy you've seen before, but it's p squared over 2m. Okay, so p squared, we have a definition of p up here, right? The quantum mechanical definition of the momentum operator right here, right? P equals h bar over I times the gradient. So now we can now express this. So we'll say, so this thing has to be multiplied by itself. This momentum operator gets multiplied by itself. And so then this is what we end up with. All right, so this p squared over 2m, it's going to have that same form in our Hamiltonian, referring to the kinetic energy. So remember, we're working with a reduced mass, right? We defined that a few slides before for mu, but it's a combination of the two masses involved. So basically, you can think of mu it's a reduced mass, but still a mass. So it's 1/2 times the mass. And so that's the same as, p squared over 2m, right? We've got a 2m in the denominator, and then our p squared becomes the momentum operator multiplied by itself. And that's going to be what we have here, where we've got h bar gets squared, I gets squared, and of course, 1/I squared. Well, I is a square root of -1, so I times I is -1, so that's going to be 1/-1. So then a -1 comes out front too. And then, of course, we've got our gradient squared. So, great, this matches perfectly, right? I've got my check marks there. We can see that the kinetic energy operator does indeed check. And it matches the intuition that we talked about earlier. So now we have a more rigorous way of looking at it. So this is our kinetic energy operator. So, of course, we know that the gradient dotted with itself, right? The dot product of the gradient with itself is this Laplacian, right? That like triangle squared looking thing, right? That's our Laplacian. And so far we've been working in Cartesian coordinates, right? Position is x, y, z. Every position that you can have is a vector x, y, z, right? It's a three-dimensional vector describing the position. But it turns out, with a hydrogen atom, there's a spherical symmetry there, right? The attraction between the electron and the proton in the nucleus is the same if the electron is, 1 Bohr radius above it or below it or whatever, right? It doesn't matter if it's above it or below it, left, right. That doesn't matter. There's a spherical symmetry. So it turns out that we really need to define our position in terms of spherical coordinates. And they both cover all of space, right? You can define any point you want in terms of x, y, and z, or in terms of spherical coordinates. So, r, theta, and phi. And we'll define that more rigorously moving forward. But it's, it can be the same space. You could just define it in different ways. And they both can give you any point you want. But if you're dealing with something with spherical symmetry, it makes much more sense to use spherical coordinates. Now, the only downside to this is that our Laplacian gets a lot more confusing, right? So here, notice that I defined the Laplacian there, right? That the second partial derivative with respect to x added to the second partial derivative with respect to y, and then same with z, right? They're all added up there. And you might think that, okay, great, that's okay, so it's just squared, right? You just kind of, it works out that way. But it works out that way in Cartesian coordinates. It doesn't do that in spherical coordinates. And we're going to show you that moving forward here. So it's not always this simple. Another thing to notice is that there are no unit vectors there, right? You're just adding these things together. Whereas by itself, there was the unit vectors there, right? And they went away. So what happened? So let's look at this in a little more detail now. All right, so here's spherical coordinates, right? So any point, instead of saying x, y, and z, it's r. How far am I from whatever the center is? So this is kind of like, if you consider, the center is in the middle of your chest somewhere, right? And you can point to something with your finger. How far you outstretch your arm, that's r. And then the angle of like how much are you pointing straight up versus straight down, that would be theta. And then phi would be spinning around, right? If you spin around a little bit and you can point in different directions, right? That would be phi. So that's basically what's going on with r, theta, and phi. Also, it's important to notice that our potential energy function is already in spherical coordinates because it's only a function of r, right? How far from the center are you, right? And again, you can kind of think about gravitational potential energy, right? If you're the same distance from the center of the Earth, it doesn't matter if you're in the United States or Mexico, you're going to weigh the same, right? If it's kind of, you can think of it that way, that the potential energy due to the charge being some distance from the electron being some distance from the nucleus, it doesn't matter the angle, it only matters r. So that actually makes sense, right? That's intuitive. And, as I mentioned, the spherical coordinates is the natural choice here, but the Laplacian is going to be a bit complicated, but it is 100% worth the trouble. Trust me on this one. So let's take a look at it. So as I mentioned, it's the dot product of the gradient with itself. That's the Laplacian. It's a dot product. So in Cartesian, let's work through that first. So Cartesian coordinates, here's our gradient, right? Again, we have the unit vectors multiplied by each respective partial derivative, and then you just add them all up. That's the gradient. And notice that's a vector, right? Because that's multiplied by, each one is multiplied by its respective unit vector. When you apply the gradient, the output is a vector, right? You've got you can kind of think of it as like different slopes in different directions, right? Like if you're walking around on some sort of terrain, right? And maybe you're standing on a hill and like it's real steep in one direction and less steep in another, right? You can kind of think of it like that. So anyway, this is a vector, right? This is a vector. But now watch what happens when we dot it with itself. So when you take the dot product of it with itself, it's basically, the first thing multiplied by itself, added to the second thing multiplied by itself, added to the third thing multiplied by itself. So that's all I've done in this first line. And this is how you take a dot product. So then now, for clarity in space, let's just look at the x dimension and simplify that. And as you can see in the previous line, like it's all the same thing, right? There's an x version and there's a y version and there's a z version, but they all do the same thing mathematically. So we're just going to do x and then assume they all work this way, which is correct. So, okay, looking at that first term, the one that has to do with x, we have x hat. And then d dx is operating on two things that are multiplied together, x hat and d dx. So we have to use the multiplication rule here, right? So if we have this differential operator, this partial derivative, d dx is operating on both x hat and d dx. Well, then it's going to be the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. Right, so the first one, so in that first term on the right there, we're taking the derivative with respect to x of the unit vector x hat. And then in the second term on the right, that's the time when we're taking the derivative of the second thing, which is, of course, d dx. So, d dx operating on d dx, of course, is just the second derivative, right? You take a derivative twice, that's the second derivative by definition. So the one on the right is really easy to explain. We say, all right, that's just the second derivative, the second partial derivative with respect to x. So that one's easy. And the one on the left is a little trickier, but not that tricky. So we say d dx of x hat. Well, let's think about that. We're taking the derivative with respect to x. So we only care about the function in the x direction here. And, well, the unit vector, what is that? That's the vector 1, 0, 0. So in the x coordinate, it's a constant. It's 1. Well, if I say, what's the derivative of the number 1 with respect to x? You know the answer. It's 0. 1 is not changing. It's a constant, right? So if you were to plot the function, right, you can make a function, f of x equals 1. It's just going to be a straight horizontal line at y, that crosses y equals 1, right? That's perfectly flat. The derivative 0. So we know that derivative is 0. There we go. So that becomes a 0. The second term, well, the second term, we have that second derivative operator, that d squared over dx squared. So that's going to hang out. But then we have the unit vector dotted with itself. Well, the dot product, again, this is the vector 1, 0, 0. So if you dot the vector 1, 0, 0 with 1, 0, 0, you got 1 times 1, which is 1, plus 0 times 0, which is 0, plus 0 times 0, which is 0, right? So you add 2 zeros to the number 1, you get 1 out of it. So that just becomes a 1, and then we're left with the second derivative operator. Again, just make a mental note of this. Remember that when we have that x hat, when I talk about the unit vector, it's the vector 1, 0, 0. And as I just mentioned here, ddx, the number 1, is 0. So, we do this with x, y, and z, and now we see why in Cartesian coordinates, the Laplacian is really straightforward, right? It's just the second derivative with respect to x added to the second derivative with respect to y, added to the second derivative with respect to z. All right, so Cartesian coordinates, Laplacian is great, nice and easy. So, and notice this is not a vector, right? The gradient operator produces a vector, but when you dot this with itself, it is no longer a vector, right? You're adding all these together. It's a scalar. So it's an operator, really. It's an operator, but numerically, if you were to take all those second derivatives and then add them together, you get a single number. You do not get a vector. So, this notion of the gradient dotted with itself in spherical coordinates, this is not so simple. So, unit vectors point in the direction that a dimension increases. And so if you think about that, right? So in x, y, and z, that's a constant, right? It's just the x unit vector is exactly, it's unit length 1 and it's on the x-axis, right? That's the x unit vector. Nice and straightforward in Cartesian coordinates. In spherical coordinates, this is not the case. This is not quite so simple, right? Because the radius, no matter what angle you're at, if you're moving away from the center, then it's increasing. So that direction is not, it's not so fixed. So you can see how these things are, they're not the same thing, right? And, to do the full derivation of the Laplacian in spherical coordinates is, it's kind of a lot, but we're not going to do a full derivation, but we will do a justification so that we're not going to just totally take it on faith there. So in spherical coordinates, this is the gradient. So notice, we still have this notion of unit vectors, right? We have the unit vector in r, theta, and phi, right? They have the little hat on them and everything, right? Those are our unit vectors. But notice that each term is not just split into just purely r, purely theta, etc., right? Look at the Cartesian one again, right? Right here, we've got x dx, y dy, z dz, right? There's no y in the z, there's no x in the y, right? They're all separate. But now notice for the Laplacian in spherical coordinates, now we've got r hat times ddr. Okay, that's just purely r, cool. The next one, we have theta hat, but there's an r in there, right? And it does have dd theta, but it's multiplied by 1 over r. And then, of course, the last one has all three, right? 1 over r sine of theta times dd phi. Okay, so things are more complicated. So, in the interest of time, professors, sometimes we're forced to kind of be like, look, this thing is true, you got to believe me, so that we can move on in the interest of time, right? But I hate to do that. So I do want to point you to another really good YouTube video. This is by Andrew Meyertholen on YouTube, and I will definitely post a link to this in the description of this video. So it would be silly for me to get screenshots of Andrew's entire YouTube video and talk through that, because Andrew's already done a great job of that. So go check out Andrew's video. So I won't go through every step of the derivation of the Laplacian spherical coordinates, though I do encourage you to do that. But just to give you some flavor of where the Laplacian is coming from in spherical coordinates, start on the left side of the screen and notice how in each case we have x hat, y hat, and z hat. And in each of these cases, note that it is possible to define each of the unit vectors, x hat, y hat, and z hat, in terms of only spherical coordinates. Right, so on the right side of all three of those equations, we see only unit vectors r hat, theta hat, and phi hat, and only variables r, theta, and phi. So there is a mapping. So the thing I'm trying to get you to see here, a mapping does exist to get the unit vectors x hat, y hat, and z hat from exclusively spherical coordinates and spherical unit vectors. So that's what I want you to get from the left side of the screen. From the right side of the screen, first we have the standard definition of the gradient, right? That's the definition we know of the gradient in our Cartesian coordinates that we know and love. But if we look at that definition, well, we can substitute out some things here, right? If what we want is we want an expression of the gradient in spherical coordinates, well, why don't we substitute out those definitions of the unit vectors x hat, y hat, and z hat, and put the definitions that we see on the left side of the screen in there. So that's why I have them underlined in matching colors, is to show you that those are equivalent, right? So if it has the same line under it, it's the same thing. It's just getting substituted in to the definition we know for the gradient. And then, of course, this isn't it. We're not done here, because, now we have an expression for the gradient that's in terms of what, like all 6 variables, right? There's partial derivatives with respect to x, y, and z. There's all 3 unit vectors from the spherical coordinates, right? So it's kind of a hodgepodge right there. It's not false. It's just less useful because right we're trying to get an expression for the gradient that is purely in the variables and unit vectors for spherical coordinates, right? That's the goal. So without showing you all of the details there, if you distribute through those operators, ddx, ddy, and ddz, and then you gather up the like terms, it turns out that you can rearrange this thing, and by knowing some definitions of how to go back and forth, you actually can rewrite that expression for the gradient so that basically all of the x's, y's, and z's go away, and you're left with only spherical coordinates and only spherical unit vectors. And again, definitely watch that video at least once. Watch him do it. He has a really great way of explaining it. Highly recommended. Okay, so we've established that this is indeed the gradient in spherical coordinates. All right, so again, we haven't proven it. If you want to see the proof, check out Andrew's video here. Again, linked in the description. But for now, we're going to say, all right, this is it. So now that this is our gradient operator, things are going to go differently when we dot that with itself, right? So we show the Cartesian one, why it is what it is. Now let's do the same thing here. Let's take the dot product of this with itself. And so now, right, let's look at the theta term, for example. When that gets dotted with itself, right, we're multiplying that term by itself, it looks like this. So this is just the theta term. So similar to how we looked at one term of the Laplacian with Cartesian coordinates and then kind of extrapolated, we're not going to quite do that here, right? Because with the Cartesian coordinates, it all works out beautifully, and they're, the process is equivalent for all 3. That's not going to be the case here. But again, just in the interest of giving you some flavor of deriving the Laplacian, and again, watch that other video so you can see the whole thing. But just to give you an idea of it, let's look at just one of these terms. So if we multiply each one of these terms by itself, right, then let's just look at theta for a moment. And that's what we have here. So again, we recall the product rule. So in terms of this, we can kind of look at that first operation, that dd theta, of theta hat 1 over r d theta, right? So this operating on these 3, right? But 1 over r, like that's not a function of theta anyway, so you might as well just group that into one of them. And so we're going to group it into theta hat 1 over r and dd theta. So there are things that, we take the derivative of the one, multiply it by the other, and then add the derivative of the other one, multiplied by the other one, right? The usual product rule maneuver here. So so if we take the derivative of the second one and multiply it by the first one, that's what we've got here, right? So if we bring this out front, now we've got theta hat, 1 over r, and then d theta. So this one's going to be nice and easy to simplify. And the next one is a little more complicated, right? Because we've got theta hat, 1 over r, and then now we're taking the derivative with respect to theta of theta hat. So, and then the rest of it, we're just multiplying it by the other piece. We're leaving the other part alone. The basically the 1 over r dd theta, right? That's being left alone in that term. Again, this is just applying the product rule for derivatives. And so we look at this, we can simplify the first term easily enough. Theta hat dotted with theta hat. Well, any unit vector dotted with itself just becomes 1. And so that goes away. So that's just a property of unit vectors. So that goes away. We've got 1 over r squared, and then the second derivative with respect to, the second partial derivative with respect to theta is the other part of that term. now the term on the right, we look at that, and remember in the Cartesian example, we thought, okay, we take the we did like d, I think it was like d dx of x hat, and that of course came out to 0, right? Because that came out to 0 because basically it's the derivative of a constant. But okay, so let's look at that here. Do we think that's going to be the case? And I love to pause and kind of think about this. Pause the video. Think about what you think the answer is here. So below I have written the definition of theta hat. So that's the theta hat unit vector there. And we see that it has an x, y, and z components here. And again, so this is sort of that sort of mixed notation where we've got some x's and some thetas and ph's and y and z, right? They're all in there. So looking at that, like this is a definition of the unit vector theta. So looking at that, if we take the derivative of that with respect to theta, do we expect that to be 0? So what do you think? No, it's not equal to 0, right? I suppose maybe if you were just trying to guess, you might think, well, maybe the terms cancel out or something. They don't, right? You can't, they don't cancel out, they don't go away. So in this particular case, d theta of theta hat is not equal to 0, not like in Cartesian. And you're probably questioning me right now. You're like, was it really worth switching over from Cartesian to spherical coordinates here? And as messy as this has been, it'd be even worse if we did not do this. So, a lot of very smart people have concluded that we need to go with spherical coordinates. And again, if you think about the symmetry of it, it makes sense. It's intuitive that this must be better. So, as crazy as this might be getting for you, this really is the best way. So it turns out that this is what the Laplacian is. So I've given you a little bit of a flavor, a little bit of a justification, not a complete one, not anywhere near complete, but hopefully you get an idea of where this Laplacian is coming from. So now if we put that Laplacian together with the Schrödinger equation, so now we have our spherical Laplacian at the top, which we just spent some time justifying, and we have the Hamiltonian, which we already knew, right? The sum of the kinetic energy and the potential energy. That's what our hydrogen atom Hamiltonian is. And right, the Hamiltonian changes depending on what system you're describing. If it's a particle in a box, it's different. If it's a hydrogen atom, it's different, right? And of course, we already knew the time-independent Schrödinger equation over there. H psi equals E psi. Pretty famous. And then at the very bottom, we can put it together and say the hydrogen atom's Schrödinger equation is the following. So one more time from the top, right? Fundamental here is the time-independent Schrödinger equation, and we're plugging stuff into that. So we have to operate on psi with the Hamiltonian. All right, you look left, there's the Hamiltonian. Now the Hamiltonian includes this Laplacian, which of course we need the spherical Laplacian because we're looking at the hydrogen atom, which has spherical symmetry. So that triangle squared right there, right? That's the Laplacian. Just imagine substituting all the stuff in there at the top defined as the spherical Laplacian into that symbol. And then that becomes the Hamiltonian for the Schrödinger equation. And you put them all together and you get equation 22.4 at the bottom, which is the hydrogen atom's Schrödinger equation. And, as is the case with solving partial differential equations, it's all about, we say, we know how the functions are changing, right? We have some expression of their partial derivatives. Right? We say, I don't know what this function psi is, right? That's the whole job of somebody who's solving a partial differential equation is to find this function or family of functions that satisfies this, right? So we're saying, all right, we know how they're changing, but we don't know what the function is, right? So the solution to a partial differential equation is a function or a family of functions, right? Like with algebra, if you solve algebra and you're trying to figure out what x is, right? When in your earliest algebra courses, that was your goal, right? X equals some number. What is it? How can you arrange things to find out what x is? Here, the goal is to find what family of functions satisfies these conditions. So what we're going to do here, so hopefully maybe you recall from the time-dependent Schrödinger equation derivation that we did, that we basically made an assumption of separability for that, right? We had like the time component and the position component. So, remember when we were splitting the time-dependent Schrödinger equation, right? We had that big capital psi of x and t, right? A spatial coordinate and a time coordinate. and we say, what if we can split this into little psi of x and a phi of t, right? And we say if we multiply these together, then that's the big psi, that's the whole thing. But we're saying that whatever this function is of x and t, it could be separated into two separate functions that are multiplied together, right? So we say this is an ansatz, this is kind of a guess. We say like, what if this is true, right? And then we can see if the solutions work out, right? Because in the end, if we make this assumption and we get these functions and we multiply them together, then they should satisfy everything, right? So basically that's what separability does for us, is it allows us to solve kind of two smaller equations and say, all right, these are solutions for the one component, these are solutions to the other. So we should be able to just multiply them together, and then now we get solutions to the full problem. So we're going to do the same thing here. But in this case, we're separating the time independent part of the wave function, right? So this is only a spatial wave function, by the way, right? Time's not even in here. So we have a spatial wave function that is in spherical coordinates, right? It's in terms of our spherical coordinates, r, theta, and phi. And we're saying, what if we can take that wave function and we're going to split it into r, capital R. This is our radial component of the wave function. And that is only a function of little r, which is the radius, right? The radial component of our position in spherical coordinates, right? We say that it's only a function of that. And the other function, y, is our angular wave function. And that's going to be a function of the two angles, theta and phi. And notice that r has a little nl and y has a little lm. What this means, those aren't variables, right? Those are parameters in these functions, right? Because as I mentioned before, I said the solutions to differential equations or partial differential equations, it's typically not a single function. Usually the answers to these things are families of functions. So different functions can satisfy it given some conditions. And so basically what we're going to have here is that there are parameters to these functions, not variables, right? You have to pick something and you set it and that's it, right? It's not a variable, it's different, it's a parameter. So we say that there's going to be a parameters n and l, and there's going to be parameters l and m. And, how do we know this? Well, because this has already been worked out before, right? This is one of those things that like people try a bunch of stuff, they get it to work out, and then later you kind of put together a narrative that makes sense of how this stuff works. So that's why that we know ahead of time that there's going to be two parameters in both of these, n and l and m and y. And by the way, that l, it's the same one. So it's not like these are two different l's. It's that same parameter shows up in both. So equation 22.4 at the top there, right? That's our Schrödinger equation for a hydrogen atom, right? We've written it down, which, it took us a long time just to write it down, right? That wasn't even solving it. We just wrote it down and said, all right, this is what it's going to be. And notice that 22.4 is in terms of little psi, right? The spatial wave function. But now we're going to split psi into that big R and big Y function. And so if we do that, so now it's ry. So in 2183, equation 2183, all I've done is I've swapped out the size for ry's to put both of those functions in there. And so, let's take notice of something here, that how the radial derivatives, right, ddr, the radial derivatives are only acting on r, and the angular derivatives are only acting on y now. So this seems awfully convenient, right? How do we get away with this? Well, the terms created by the product rule all include the derivative with respect to a variable that's not in the function, right? So then that's going to go to 0, and then they're going to cancel out, right? We've seen this before, and this is something that separability is helping us out with here, right? Assuming that this is separable. So we make that assumption and we go with it until, something maybe would indicate that it doesn't work. And it does work here, right? That's why it's part of how we teach it. We know it's going to work. So in this next step here, then we simplify things a bit. So we say, all right, let's group these things together so that we have a bunch of stuff that's only a function of r added to a bunch of stuff that's only a function of the angles theta and phi. So in going from 2183 to 2184, we say like, all right, first, how about we divide everything by ry, right? So we divide every term on both sides by ry. That'll simplify things a little bit. Then you have e by itself, and then you bring e to the other side, right? We subtract e from both sides. And so now it's set equal to 0. So in equation 2184, everything is set to 0. and we've kind of grouped things conveniently. And what makes it convenient? Well, we've grouped it in such a way that the first term on the left is only a function of r. There's no angular stuff in there, right? And then the function on the right, the only variables in there are the angular ones, theta and phi. So we've got an r term added. We have like a radial term added to an angular term. So again, we're going to use that same trick that we used for deriving the time-dependent Schrödinger equation, right? We've got, basically in equation 2184 here, right, where we say that we have this stuff that's exclusively r. We have a set of terms that are exclusively r, another set of terms that are exclusively angular, theta and phi. Well, then that means I could put all the r stuff on one side and set it equal to all the angular stuff. Well, r and theta and phi, if I just change theta and phi, right? Let's say I just change theta and phi. I can't change r that way, right? If you think about like moving around on the surface of a sphere, right? No matter what I do to theta and phi, r is the same. If I say I'm confined to the surface of a sphere, so then that means you've got some degrees of freedom that like you're moving them around, and you can move them around all you want, and you can't affect the other side, right? So think about that. So if these things are equal to each other, then that must mean that both of them independently are equal to a constant. And again, we went over this in the other video where we derived the time-dependent Schrödinger equation. So, so why do we set it equal to L times L plus 1? Well, again, one of those things where like, all this stuff gets figured out in a very circuitous manner, and then later we put together a story that we know is going to be more cohesive when we teach it. But all we really would know if we didn't know that, if this hadn't been done before, right, we would just know that they were both equal to some sort of constant. But it turns out that that is true. And those constants work out in this pattern. So we might as well set it equal to that because that's the direction we know it's going, right, because of prior work. So in equations 2185 and 2186, that's what we're seeing is we're just breaking this into two separate partial differential equations. So let's take the angular portion first, right? So we've split this into two smaller problems. Let's at least try to understand a little, get some intuition for how this is solved. So looking at just the angular portion, that's what we have on the slide here at the very bottom. That's only the angular portion. And basically, all we've done from 2186, we've multiplied both sides by y. So of course, the first thing we did in going from equation 2186 to the one you see below by the blue arrow, we've just multiplied both sides by y, right? So both sides by y, and then we've got what we see below. And so it turns out that in this form, this is actually the eigenvalue partial differential equation whose solutions are the spherical harmonics. And what are spherical harmonics? Well, they're super cool looking, and we're going to talk about them moving forward a little bit. But for now, just the main point that I'm making at the moment is that this is a known PDE, right? This is a previously solved partial differential equation. This is one that we know it has a solution in this form, and often that is another one of the tricks in the bag of tricks of people who solve differential equations or partial differential equations is, can you rearrange something so that it looks like something with a known solution? And so this is a trick that's used all the time, and so that's kind of what we're using right now. And so in this form, there's basically the spherical harmonics are the known solutions to this problem. And we have a more compact way of writing it as well, where that capital lambda, right, the thing that almost looks like a triangle but it's missing a side squared, right, that's a lambda. So we're saying that lambda squared is what we're replacing here. And then of course lambda squared is defined below, where basically, it's most of the stuff in the brackets, right? So it's basically that thing operating on y. So you look at that entire thing as an operator operating on y, and then you get the thing that's inside the square brackets. So, basically this y of Lm, where Lm are parameters, but y is a function of the two angular degrees of freedom, theta and phi. And so the name that we give that capital lambda squared is, we call it the Legendrian operator. So again, we've shown that, rather than an all-out derivation, this is more of a justification. where we have rearranged things in such a way that they are a differential equation with a known solution, and basically we can kind of group all of those things together as the Legendrian operator, right? That the thing that looks like a triangle squared with a side missing out of the triangle, right? Which again is a capital lambda. And so if you look at equation 22.6, that's certainly much easier to look at. And you say, okay, we have an operator. The Legendrian operator operates on y, and then you get y back out multiplied by minus L times L plus 1. And again, this has that sort of similar flavor to the Schrödinger equation, right? Where you have the h psi equals E psi. So you operate with the Hamiltonian and you get out an energy. Similar idea here, right? And this L minus L times L plus 1, that's more like that's like the eigenvalue here, right? Which was energy in the regular Schrödinger equation, h psi equals E psi. So perhaps more satisfying than looking at some of the math. Here is what this looks like. And so the only thing changing from all these, so these are all different functions that are solutions to this. So again, this idea of solving differential equations, you're looking for functions that satisfy that. So these are the functions known as spherical harmonics that satisfy these conditions, that when we operate with the Legendrian operator on the angular wave function y, these are the functions that will make that statement true at the top right. All of these functions will do that. So what's different about the different functions? Well, L and M, those parameters. And again, the quantization, right? So they're quantized. They're integers that can be plugged in for L and M to make these things true. And there's some constraints on them too, and we'll talk about that moving forward. But I just wanted to take a moment to sort of appreciate how cool these things look, and that these wave functions are the solutions to the equation at the top right. So again, these functions are called spherical harmonics, and they are solutions to the angular wave function at the top right. Okay, so now let's look at the radial portion of the wave function. So that's the one at the top, 2185 in the box. So let's look at that and try and justify that to ourselves a little bit. So equation 22.7 is really at 2185, but using the reduced mass instead of the regular mass m. So that's the only difference there. And so this notion of like, can I take a particular differential equation and manipulate it somehow to make it look like one that has a known solution? And if I could do that, then I could just use that known solution and be like, well, now it's this, right? You take one problem and you manipulate it until it looks just like another problem that you already know how to solve. This is such a commonly used trick in science. Everyone should know about it, right? This is a great trick, and in mathematics too. Really, it's mathematicians that came up with this approach. Okay, so with that in mind, it's not at all obvious looking at this thing, right? You wouldn't. It would probably take you years to guess this if you ever got it, right? But it's actually easier to solve this if we define P of R as little r times big R of R. If we define a new function that's P of R, and what's P of R? It's just our regular radial function R multiplied by its variable, right? So if we have some function f of x and then we multiplied f of x by x, that's what we did. That's all we're doing. And we're saying, and we give it a name. So we give it the name capital P of R. So this is our new equation that we've defined. And then, then big R of little r is equal to big P of little r divided by little r, right? Just bring the r to the other side. So it's easy to get from one form to the other. So then we just have to plug that in and rework equation 22.7 so that it's in terms of this big P function rather than the big R function. So that's all that's gone on there. And we also noticed that, some algebraic manipulations also been done, right? To get EP by itself on the right side, which is going to be useful to us later as well. So that's just, again, some algebra also went down between equation 22.7 and equation 22.9. So now that we have this function, let's try and solve just the radial portion of the wave function. Well, if we look at this, does this look at all familiar? Don't feel bad if it doesn't. This stuff is not obvious, right? There's a Feynman quote. I forget exactly what it is, but it's something to the effect of, if you don't find quantum mechanics confusing, then you haven't even begun to understand it, right? This stuff is confusing. If you're not confused, you haven't thought about it hard enough because it's confusing fundamentally. So anyway, so maybe, pause the video, think about it for a little bit, And, does this look familiar? That, okay, we're operating on something P, and then we're getting out an energy multiplied by P. So we're getting P back out on the right side, right? Multiplied by an energy. Operating on a function, getting that function back, multiplied by its energy. I bet maybe you know what it is now, right? It's the Schrödinger equation. This almost looks exactly like a Schrödinger equation for a one-dimensional system. But this function that we kind of made up, right? This capital P of R, which is really just our regular R function, big R function multiplied by its variable little r, is standing in for psi of x. And, maybe this isn't super surprising if we kind of think about it, because, this is the radial distance. So kind of like, okay, if we're only thinking about one distance or a particle in a one-dimensional box, right? You can see how like this, okay, this kind of makes sense. And really the main difference, if we look at like, open up the other video or look at the Schrödinger equation for a one-dimensional particle in the box, take a moment and compare them. And really the difference that we have is, the main difference is that now we have this L times L plus 1 h bar squared over 2, this thing right here, right? Now that is inside of these brackets. And basically the way we can think about that, we can interpret that and say that, well, maybe we can think about this, we can justify it to ourselves as a correction due to the centrifugal repulsive force pushing away from the nucleus. So think about Bohr, right? Bohr, he didn't quite have it, but boy, he was really in the right direction because he had a similar thing, right? He said, okay, what if the centripetal force and the attractive force are balancing out and keeping it in orbit? It's like the moon going around the earth. It's not that, but boy, it sure has a very similar, it smells similar, right? So basically we have that added in there. And so you can think of it as, notice the first term, the minus e squared over 4 pi e naught r, right? That's negative. So then adding this makes the total of the stuff inside the brackets less negative. It weakens it, right? Because that minus e squared over 4 pi e naught r, that's the attraction due to, the two charges, right? That's Coulombic attraction. And so basically this is weakening the Coulombic attraction. We can think of it as being due to the centrifugal repulsive force that's pushing it away from the nucleus. So the charge is attracting it, but the centripetal force is pushing it away. So it's having a weakening effect. So this has a really nice form in that, we can kind of justify it to ourselves like this. And of course there's, we can also find more compact ways of writing this as well. So, if we define that kappa, that 2211, that equation 2211, we say like, all right, let's define something called kappa. And it's going to be this, minus 2 mu e square root of that over h bar, and substitute it into equation 22.9. Then we have 22.12 here, and it doesn't look like it really helped all that much. Right now there's a cap in there, but there's some other things too, but we'll keep going. It gets better, right? So right now it looks like that, but we can make it a little more simple. So let's also define something called rho and rho naught, right? So that thing that looks like a P, it's a rho, it's Greek rho. So rho is going to be kappa r, and rho naught is going to be all of that right down here, right? This is going to be rho naught. So if we define these two things, now we can define things even a little more compactly, and we substitute those in, and ultimately we can write the equation as 2214 down there, equation 2214. And so now we have a differential equation in terms of rho, and we say, all right, the second derivative of the function p, capital P, with respect to rho, right? Second derivative of p respect to rho. And notice, by the way, that's not that funny little d for a partial derivative. That's a regular d now, right? Because this is only a function of r, right? But of course, we've made more substitutions, and now it's really a function of rho. But nonetheless, it's a function of one variable. So now derivatives are just derivatives, right? They're not partial derivatives. So the second derivative of capital P with respect to rho is equal to what you see on the right-hand side of 2214 there. So that obviously looks a lot cleaner than we've seen before, and maybe, we can kind of see the effects a little bit more. So now we're saying like, okay, if we take the second derivative of this function p, we get that function back multiplied by 1 minus rho naught over rho plus L times L plus 1 divided by rho squared, right? So we have all that in front of a p. But again, think about the Schrödinger equation, similar kind of form now. We're saying, all right, take a second derivative of some, I'm looking for a function rho, I'm looking for a function capital P that if I take its second derivative with respect to rho, I get that same function back multiplied by all that stuff in the square brackets of equation 2214. And again, all these things that we've done to kind of like massage this equation into something else, right? It looks different, but it's still equivalent, right? It's still equivalent, but it looks different. Now we can recognize this as like, oh, these have known solutions as well. So this was something that was already discovered by mathematicians, and these are called the Laguerre polynomials. And so the solutions to equation 2214, right? That's a differential equation. If we solve that differential equation, we get Laguerre polynomials, which are functions big R of little r, right? The function is called big R. Its variable is little r, and it has two parameters, n and l. And these things end up being quantized, right? So, we see where things are going, right? Remember, way back in the beginning of this, we had some quantization, right? When they were trying to first justify the emission of hydrogen, the emission spectrum, right? The quantization, we just said, like, well, we have integers, I don't know why. Well, now we have mathematical form that the quantization emerges from it by itself, right? Nobody said it has to be this way. We said, well, we know how the function must change. And if it changes like that, there's going to be a family of functions that satisfies that. And when we say a family of functions, we mean these functions that have these parameters that can be changed, right? And they're constrained to integers. But they're constrained integers by the solution to the differential equation. Nobody made it be that except for the differential equation itself, right? So it's emerging. The quantization is emerging from the mathematics now. So now we have the radial component. So first we solved for the angular component, and now we have the radial component. And as we said, the strategy of using separability to solve partial differential equations is that in the end, we're solving separate problems, and multiplying those separate solutions together is going to give us the complete solutions to the original problem at hand. So again, going back to equation 22.5, right? We call it an ansatz, right? We say like, let's just assume that this thing is separable, right? That the part that's a function of r is not affected by theta and phi, right? So therefore we can separate it into these two things. So basically we have these two functions, one that is only a function of the variable r, which is big R, and the other function, big Y, is a function of the other two variables, theta and phi, the angular variables. And there are three parameters present, n, l, and m. And notice L shows up in both of them. It does have to match for those two. But basically, you can choose three quantum numbers here. Oh, no, notice I said quantum numbers. So we can choose three integer values, n, l, and m. And there's going to be some constraints on them, but we can choose them and plug them in, and these are all going to be valid solutions. So again, these are much more satisfying to plot and look at what they look like than it is to look at the equation sometimes. So let's take a look. So this is really cool. Basically what we have here is an animation. I have the citation there at the bottom from Wikipedia. And basically you see it cycling between different values of these three integer values for n, l, and m sub l, right? And you're seeing density plots. We're not actually looking at the wave function psi, we're looking at the density that you get from multiplying psi star by psi. And again, in previous videos where we solved the Schrödinger equation, we've talked about what this is. But you can think of this as probability densities. If you ask the question, where's the electron, right? Well, first of all, it depends what level you're in here, right, for n, l, and m. But given those values, if you ask the question, where's the electron, basically the brighter it is here, those are the spots you're most likely to see the electron. And spots that are completely black, you will never see it there. And one thing that's very interesting is notice how some of these bright spots are completely surrounded by black. So that means that the electron can go from places it's allowed to other places it's allowed that are separated by places where it's never allowed. Which, I think you just really have to take a moment and think about that, because again, it's one of those things, if you don't find it confusing, you haven't thought about it hard enough. But this is fascinating stuff. So, we're just cycling through a few of the solutions, and that image on the left there, the blue with the, the blue plane passing through a red sphere, that's just an idea of what a cross section is, right? So if we take a cross section right through the center of that thing, that's what we're looking at on the right. We're just looking at the cross section. So you're looking at like what would be on the plane. And so here are a few others, right? So I think it's cool to watch it cycle through with some of them switching, etc. But here are some other ones with different choices of those three integer values. An important thing to note too is that, this does form an orthonormal basis set. So we have these Kronecker delta functions, NN, LL, and MM all the way right. This is basically saying that these wave functions with these three parameters, N, L, and M, right, and they all match, then those Kronecker deltas are all equal to 1, and you get 1, right? But if any of those are 0, then obviously if you've got a 1 multiplied by 0, you're still going to get 0, right? So these all have to match. If they don't match, you get 0. And so basically this is a property of an orthonormal basis set. So I've mentioned a few times that these parameters, N, L, and M, they do all end up having to be integers, right? The legitimate solutions, the solutions don't work out unless they're integers. They're not legal solutions unless these numbers are integers. And I also mentioned that they're a little further constrained than that. So that's what we're going to look at now. So let's look at how N and L are related. So basically, N can be anything, right? 1, 2, 3, 4, any integer. Starting with 1, right? And then L can have any value that, again, an integer from 0 up to n minus 1, right? So if n is 3, the highest L can be is 2. All right, and so just as L is kind of locked in, or it is locked in, right? It can go from 0 up to 1 less than whatever n is set to. M sub L, the third quantum number here, that also has some constraints on it. And it's also integers, and it can range from negative L to positive L. So whatever you choose for L, that limits what M sub L can be. So M sub L can only range from negative L to positive L. And by the way, so these all happen to be integer values, and they're quantized, right? So the important thing with quantization, you can't have stuff in between, right? There's no 1 and 3/4, 1.5, whatever, right? These are all integer values. That's a quantization here. But I don't want you to think that quantization can only be integer values, right? If you have some sort of parameter that can only be, let's say, negative 1/2 or positive 1/2, those are the only choices. That's still quantized, right? Those are not integers. 1/2 and negative 1/2 and positive 1/2 are not integers. But the important thing is that you're not allowed to do like negative 0.4, right? So it's still quantized. You have a choice. It's negative 1/2 or positive 1/2. That's it. So by the way, I want to make sure I clarify that quantization just means nothing in between, right? Okay, so let's look at degeneracy. And we'll define that a little moving forward, but let's look at what it is here. So degeneracy, this is a function g of n. And basically, with this g of n is a summation of 2l plus 1. Basically, this is based on those three rules that I gave above, right? 22.5, 22.16, and 22.17. A consequence of this is that the degeneracy is going to be that summation, which can be simplified to actually be n squared. So let's look at an example. This is much easier to see with an example. So if n is 3, then the degeneracy must be 9, because 3 squared is 9. And well, let's enumerate them all out. So if we set n equal to 3, and then let's say L is allowed to be 0, so let's choose 0 for L. Well, M can only be negative L to positive L, right? Well, 0, negative 0, positive 0. Well, okay, that's just 0. So 3, 0, 0. So that's that top row. Then the next row, let's say, okay, we're sticking with n equals 3. That we're holding fixed for this entire thing. But now let's say we choose 1 for L. Well, so notice that second row, the second number is 1 for all of them, but we can only be negative 1 to positive 1. But we're allowed 0 too. So negative 1, 0, 1. Okay, so there's 3 possibilities there. And then likewise at the end, if we choose 2 for L, now we can go from negative 2 all the way up to positive 2 in integers. So we get 9 different possibilities here. So it's kind of how many different possibilities do we have with degeneracy? The number of ways to get something. Well, the number of ways to get what exactly? Right? The number of ways of getting something has to do with degeneracy, but it's kind of an incomplete definition. Well, here's your big hint. Notice the energy function. So the energy function that emerges from all of this math is equation 2219 there, right? So energy only depends on the principal quantum number n. So the energy of the system only depends on n. If we think about this, all right, maybe this makes some kind of sense. That, again, think about back to Bohr and thinking about things orbiting. Again, they don't orbit, but, the distance the charges are separated, kind of similar to gravitational potential energy. How far up are you, right? The higher you climb on Earth, the higher your gravitational potential energy is. So, this n, that kind of determines how far out the shell is, right? That's kind of how we think about n. And so this is what completes our definition of degeneracy. It's the number of ways that we can get a particular energy. So we've covered so much theory here, right? And we've got 3 quantum numbers out of it. 3 quantum numbers just emerged here, right? We've got our principal quantum number n, we've got our azimuthal quantum number L, and we've got our magnetic quantum number m sub L. So maybe when you took general chemistry, you were told, all right, there's 4 quantum numbers that can completely define the state of an electron in an atom. And that's true, right? But you were just kind of given that. Now you've kind of earned a little more, right? This is one thing I'm so big on in physical chemistry, is now we kind of earn the equations that we were just sort of given before. So let's think about it. Which one's missing? If we've got the principal quantum number, the azimuthal, and the magnetic, what's the one we're missing? Maybe pause it, think about it, see if you can remember which quantum number we're missing. Think about those little arrows you draw up and down, right? Right, we're missing spin, right? M sub S, we're missing spin. We don't have spin. So it turns out, so the Schrödinger equation gets so close, and again, this was worth a Nobel Prize too, right? This was much closer than the Bohr model, and the Bohr model was much closer than just, empirically guessing. So, things got progressively better and better. And these huge steps forward in our understanding have been recognized as they should be. But the next step to get even more detail and to get spin to emerge from this, we actually need something else. We can't use the Schrödinger equation. We need the Dirac equation. Or at least we can't use the standard Schrödinger approach. We need a Dirac equation. And that's outside the scope of this course. And this video, certainly, that's outside the scope. But basically, I put this quote from Professor Koleshinsky's book in here that describes the Dirac equation a little bit. And basically, it shows us how to fix where the Hamiltonian, it gave us 3 out of 4 quantum numbers. Amazing. But the Dirac equation gets it the rest of the way. And so, as I said, we're not going to cover the Dirac equation, but I am going to include a way to make a correction to the Schrödinger equation that you can use to get a little bit closer. So we're going to use another trick that's used often in physics called perturbation theory, and in physical chemistry as well. So this is called perturbation theory. And the concept with this is that you sort of take an approximate description and you add some stuff to it, typically of polynomial form, where each thing you add to it is maybe a polynomial of a higher order, and those higher orders, they tend to shrink, right? So that as you keep adding more and more, so think about like maybe a Taylor series, if you've heard of a Taylor series. But anyway, I'm saying too much about perturbation theory. Look at equation 2222, and we see that our Hamiltonian is defined as H naught. So H naught is our regular hydrogen atom Hamiltonian that we've been working with, right? Remember, it had the kinetic energy component added to a potential energy component. And so that's what H naught is. And then we're adding these corrective terms. And so there are 3 terms that get added in this perturbative treatment of the Hamiltonian that can be used to get the Schrödinger equation closer to what the Dirac equation can tell us. So this H of M, this equation, this accounts for the relativistic effects due to the inertia of the electron due to velocity, right? So we say, okay, if the electron's moving, it must have some inertia to it. And so we want to, so that accounts for some of that. And H hat of D, so this is known as the Darwin term. It is a relativistic electric moment of the electron and non-localizability. So that's a lot. But basically to say, like, what's the major difference between Schrödinger equation quantum mechanics and Dirac equation quantum mechanics? It's relativistic effects, right? We've completely ignored relativity in the Schrödinger equation. Dirac accounts for relativity. So this term is to account for relativistic effects. And finally, at the bottom, we have this H hat of SO. So this is the spin orbital interaction of the intrinsic magnetic moment of the electron and the magnetic field generated by the orbital motion of the electron as it moves in the electric field of the nucleus. All right, so as the electron's moving in the electric field of the nucleus, basically we're saying that the spin and the angular momentum due to the other quantum number, right, m sub L. Basically, they're affecting each other. And a macroscopic thing I can tell you about, it's not the same, but you can kind of think of it as being analogous, is if you have a gyroscope, right? If you've seen a gyroscope and you pull the string, that's spinning, right? It's spinning about an axis. And then if you take that and you want to move it through the air any old which way, the fact that it's spinning affects how you can move it around, right? It kind of fights you in some ways and it allows you to move more in other ways. So the gyroscope's intrinsic angular momentum is that it's spinning one way, but then you can grab it and move it in different ways, and it'll fight you in one ways and allow you to move in others. So that's kind of how I like to think about like this interaction, right? That what this interaction is. And that's why we call it spin. And now, electrons are not spinning. They're not spinning like a gyroscope, but it's convenient to think about it that way. You know, just like they're not in orbit, but boy, it was convenient to think about it that way and build up from there. So, you know, the only reason I wanted to show you this page is because we had 3 out of 4 quantum numbers, and I wanted to briefly touch upon spin in here because there is a way to get it to emerge from the mathematics. The full way to do it is with the Dirac equation, but we can use a perturbation theory approach here and add some effects to a regular Hamiltonian so that we can get a spin effect in there as well. All right, so congratulations for making it this far. We've now covered all the material that we are going to cover in this particular video. So I wanted to take some time and go over some main points. So starting from the beginning, the Bohr atom was a great first guess, Nobel Prize level great, right? It was worth a Nobel Prize. So was it quite right? No, but it was a really nice approximation, so much better than what was before it, that was worth it. That was well-deserving, very well-deserving of a Nobel Prize. And it's a way of explaining the mechanics of the hydrogen atom. But the inaccuracy is assuming orbital mechanics, that like basically the electrons are in orbit. They're not in orbit. And so, one of the big innovations is that Bohr said, well, I think angular momentum is quantized. And then that's going to tie in to the quantization that we see of some wave numbers of emission being allowed and the rest of them not being allowed. And while this was definitely better than just sort of empirically placing that constraint and being like, well, this is what we saw, so this has to be an integer. It was definitely better. But nonetheless, he did kind of put that in there, right? He said, okay, angular momentum has to be quantized, right? Therefore, the energies that we see are also quantized. So again, amazing discovery. And then, of course, just to remind you, the emission spectrum of the hydrogen atom was first measured by angstrom. And of course, I put a picture of the Bohr atom at the bottom right, which, although it is not quite correct to say that these things are in orbit, it looks so cool, right? I always think of The Simpsons, and it's an iconic looking symbol. And honestly, how do you draw a delocalized electron? You kind of can't. So we're kind of, this looks nice. And although the probability density functions are a very cool way to do it, you kind of need a computer to make those look nice. You can't really do those by hand very well unless, you're very skilled and you have a lot of time. All right, so next. So although Bohr did quantize angular momentum, it was just sort of a decision. He was, I'm building the model, I'm quantizing angular momentum, and that's just the way it is, right? But now we say, well, okay, the quantization was there, but it was just sort of decreed. But now we're saying, all right, the typical way to do quantum mechanics is to solve the Schrödinger equation. So let's come up with a way to describe the hydrogen atom by solving the Schrödinger equation. And this way, the quantization should just emerge, right? It should just emerge from the differential equations. We don't have to decree, all right, this is quantized, right? It'll just happen, which makes it a better mathematical model, right? The fewer constraints you have to put on your model, the better, right? If things just emerge that are also experimentally known, like that's what you want, as much as you can. So if we solve the time-independent Schrödinger equation, h psi equals E psi, for a wave function psi that describes the quantum state of an electron trapped by its Coulombic attraction to the nucleus, that's what we're doing here, right? So if we compare this to a particle in a box, rather than saying, all right, we've got this, this infinitely strong box and there's a particle stuck in it, all right, that is a way to trap a particle. But now we have a more physically justified description of how an electron could be trapped by its attraction to a positive nucleus. And so again, looking at the Hamiltonian, we see that term on the right. That is the Coulombic attraction. That's the potential energy function. And so basically, that's the potential energy term of the Hamiltonian. Next point. Due to the spherical symmetry of the Coulombic attraction of an electron to the nucleus, the only reasonable decision in terms of a coordinate system is a spherical coordinate system. And perhaps when you got to look at the Laplacian in spherical coordinates, you're sort of questioning me there, like, really? This is the best thing we could do? Yeah, it really is. But yeah, as you see in the first term, the kinetic energy term of the Hamiltonian, we need to have the Laplacian in there, right? That triangle squared thing, right? That's our Laplacian. And so it has to be there. So we need a Laplacian and we need spherical coordinates, and putting the two together is totally doable, but it can be tricky to derive. So we sort of justified it without doing a full derivation. And again, watch that other video that is linked in the description where they go through the entire thing. It's worth watching it at least once. But point being, there's a kinetic energy term in the Hamiltonian, and it has a Laplacian, and it needs to be in spherical coordinates, and it is worth the trouble, trust me. All right, so another main point. So this slide is the one where we brought everything together, where we have our Laplacian in spherical coordinates at the top there. We know the Hamiltonian for the hydrogen atom below that, and then below and to the right, we have the time-independent Schrödinger equation. Right, so there's no time in there. It's just h psi equals e psi. This is our spatial piece of the Schrödinger equation. And then if we put all of this together, right, you plug the spherical Laplacian into the Hamiltonian, where the Laplacian is shown, right, triangle squared. Plug that all in there, and then plug that h, right, that's our Hamiltonian. Then you plug that into the time-independent Schrödinger equation. Then you get the equation at the very bottom, 22.4 there. So all of that was just to write down the Schrödinger equation, right? That was just to figure out what is the Schrödinger equation for the hydrogen atom. It took all that work just to figure out what it is, but we still need to solve it, right? So a solution to the Schrödinger equation is any function psi of r, theta, and phi that satisfies equation 22.4 below, right? So the hydrogen atom Schrödinger equation is below. Any function psi of r, theta, and phi that satisfies that is a legal solution. And as we've seen, there are many solutions, right? There's really infinite many solutions if you keep going up in the principal quantum number n, at least from a mathematical perspective. So when tasked with solving this partial differential equation, we went to the same trick of separability that we imposed in solving the time-dependent Schrödinger equation, where we basically said, okay, we want this. So back then it was capital psi, right? Capital psi is going to be your spatial wave function multiplied by your time wave function. So we split space and time into two separate components that get multiplied together. And basically you solve each of those differential equations separately. And then basically if you have those two separate solutions and separability holds, then you can solve them independently, and any wave function that solves the one, and then you choose a solution from the other, you can choose any pair of solutions and multiply them together, and they work. So equation 22.5 at the bottom, we show our spatial wave function psi, right, time independent, is split into an only radial component, capital R, and an only angular component, y. So basically we can solve those differential equations. You can solve a differential equation to get big R and solve another differential equation to get big Y, and take solutions from each one of those, multiply them together, and you've got a solution to the entire thing. That is separability. And granted, you can't always assume this holds, but here it does, so we do get away with it. So this slide shows in a little more gory detail of how separability works for us. So basically, so equation 22.5 is the separated version, right? So we just take r times y and substitute that anywhere you see a psi in equation 22.4, and that gives you 2183. So then from 2183, if we divide both sides by ry and then bring the e over to the other side, we've set everything equal to 0 in equation 2184. And just as importantly, we've got one term that is only a function of our degree of freedom, little r, right? Our variable little r. So that first term, notice there's no thetas or phis in there, right? And then the other one has only thetas and phis and no little r's. So basically we've separated the radial components and the angular components. And what's interesting about this, so, because that's set equal to 0, I could just bring one term to the other side, right? One of those collection of terms to the other side and be like, okay, this R stuff equals the angular stuff. And because you have two things like that are not connected, set equal to each other, right? Like I could change theta and phi all I want, but that won't change R directly, right? Again, like if I'm constrained to the surface of a sphere, and all I can do is change those two angles, that's not going to change R, right? So you've got things that are not directly affecting each other, but they're set equal to each other. Well, then that actually means, this implies that they're both equal to a constant. And that's exactly what happened when we used separability to solve the time-dependent Schrödinger equation. So if you're a little fuzzy on this, maybe rewatch that video. So 2185 and 2186 is basically taking 2184 and breaking it up into two separate differential equations to solve. And notice that we set the constant as L times L plus 1. And again, this is something that, if you were deriving this for the first time ever, this isn't something you would intuitively do. It's just something that we know how it's known where this is going. So we set it up this way. I could have set that up to any constant, but it might as well be the constant L times L plus 1. So now that we've separated our partial differential equation into two separate ones, let's solve one of them, right? So first, we chose to solve the angular wave function first, or at least show how it can be solved, right? And for this one, after some algebraic manipulation, we found that we could define an operator that we call the Legendrian operator, which is that capital lambda squared, that, looks like a triangle with a side missing, right? The Legendrian operator operating on our angular wave function gives us that same wave function back multiplied by a constant, and that constant is minus L times L plus 1. So, again, this has a similar flavor to our Schrödinger equation, our time-independent Schrödinger equation of H psi equals E psi, right? It has that similar kind of flavor. You operate on something, you get that something back, but now it's multiplied by some constant, right? Same kind of deal. And what's really cool about this is that these are known solutions, right? This is a known differential equation, and the solutions are what are known as spherical harmonics. And this figure shows you what some of these spherical harmonics look like for different choices of the quantum numbers that are involved in it, right? So that you can set the quantum numbers to different values, and these are the different spherical harmonics that you can get out of it. So the wave functions are spherical harmonics. That's what they are mathematically. All right, so now let's look at the radial wave function. So looking at the radial wave function, that's 2185 at the top there. We can actually solve this more easily if we define a new function that's capital P of R. And what's capital P of R? It's just our big R of little r that we've had before, but now we multiply that by R, right? So that's what that is. And so if we define capital P of R like this, and we want to substitute that into the equation, anywhere you see a big R of R, you can plug in a big P of R divided by little r, right? And then then you can just swap those out because they're equivalent. That's how we defined it. And so that seems like kind of a nutty thing to do if you're not familiar with this sort of thing, but it actually does make the problem easier to solve. And looking at this, we realize that this looks so much like the solution to the particle in a box, which, I feel is a very satisfying result. And again, now we can put them all together. And if we put both of these solutions together, that's the complete solution. All you have to do is multiply the two together. And so then we see that for these different values of n, l, and m sub l, we get all of these different wave functions that if you multiply that wave function, right, psi star by psi, you multiply the wave function by its complex conjugate, you get a probability density function. And then we can use that to answer the question, where's the electron, right? All we're trying to do is figure out where's the electron. And well, the answer is like, well, it's complicated. We know where it's most likely to be and where it can never be, right? And again, notice that we have nodes, right? We have places that are completely black, and they have non-zero probability on either side of the black parts, right? So there's black parts that completely separate the places where there are bright spots where the electron could be. So basically, you measure the electron. It'd be like if let's say you walk out of the room and your dog is on the left side of the room, and then you walk back into the room and your dog is on the right side of the room. You can certainly assume that at some point he crossed the center of the room, right? But that's not the case with a quantum particle. And I just think that's wild. And up next, I'm showing this slide again because I want to remind everyone that we can't just set these quantum numbers to any value we want, right? There are constraints. And we didn't make these constraints up. No one imposed this on the system. It emerged from the mathematics of solving the Schrödinger equation. So if we choose a value of n, right? N can be any integer, 1 or greater. And then L can go from 0 up to 1 less than n, and of course must also be an integer value. And m sub L can range from negative L to L and must also be an integer. Then finally at the bottom we show the degeneracy equation that tells us that the degeneracy of any value for n is going to be n squared. So what do we mean by degeneracy? Basically we're saying that these other choices of quantum numbers, if, for example, we choose n equals 3, then there are 9 different ways that we can set all of the quantum numbers to follow all of these rules that have emerged. And then physically, really the degeneracy is the number of ways that we can achieve the same energy, because it turns out that when we looked at the equation that tells us the energy of a particular state, the only quantum number that appears in that equation is the principal quantum number, n. Right? That's the only one that shows up. Therefore, the energy is determined by that quantum number. And therefore, the choice of the other quantum numbers does not affect the energy of the hydrogen atom. So it's the number of ways to achieve that particular energy level. So at this point, we have now justified 3 of the 4 quantum numbers that can completely describe an electron in an atom, right? It only takes 4 quantum numbers to completely describe basically what's going on with an electron in an atom. We got 3 of the 4 just emerged from the mathematics using the Schrödinger equation, and that's an incredible discovery. The only one that was missing is spin, right? So when back when you took general chemistry, you remember drawing those diagrams with the up arrow, down arrow, up arrow, down arrow, right? You draw those arrows up and down. That's the spin up or spin down. And for a really rigorous treatment of where spin comes from, you really need the Dirac equation. But that is too much for this course, too much for this video. We're not going to do it. But I at least showed you an approach to getting it using perturbation theory. And that's what we see in this perturbative correction to the Hamiltonian in 2225 down there. So that is the term that involves spin. So we've covered quite a bit. So I think it's important. Now let's just take a moment to appreciate the massive effort that it took from some of the smartest people who ever lived just to get a mathematical description of the simplest object in all of chemistry, a single hydrogen atom. Right? If you want a detailed mathematical description of what's a hydrogen atom, or more specifically, what's the electron doing relative to the nucleus in a hydrogen atom? Seems like that, this is the simplest object in all of chemistry, and you see how complicated the math gets. And, even after all of that effort to solve the Schrödinger equation, those standard solutions that are still a little off because they don't account for relativity or spin, right? We need the Dirac equation for that. And again, the Dirac equation, outside the scope of this course, I want you to know about it, maybe read something about it if you're curious. But honestly, the accuracy you get from the Schrödinger equation is quite good for most, and that's a strong most, chemical applications. So I thought we would end with maybe a couple inspiring quotes. So here's one from Dirac himself, and the website where I found this is below. And basically, I think it's interesting. He actually started out in electrical engineering and then studied applied mathematics. So not a physicist, not a chemist. He's an applied mathematician who came from electrical engineering. And he said, "I owe a lot to my engineering training because it taught me to tolerate approximations. Previous to that, I thought one should just concentrate on exact equations all the time. Then I got the idea that in the actual world, all of our equations are approximate. We must just tend to greater and greater accuracy. In spite of the equations being approximate, they can be beautiful." And I love this, right? Because, when we're doing theory, we're always making approximations. And, this isn't just physical chemists. If an organic chemist talks about a bond formation, or maybe they draw a reaction mechanism, those are huge approximations, right? Those aren't actually reality. But does that mean they're bad or useless or terrible? No, they're amazing. Think of all the amazing medicines that have been created by organic chemists because they did things using reaction mechanisms to justify what they're doing. They're making tremendous approximations when they think about molecules moving the way they think about them moving. That's not actually what they're doing, but it's, you know, it's close enough to be useful, close enough to be beautiful, and I think that's great. So again, the arc of the story in terms of this presentation, right? We started with, you know, explaining the emission spectrum of hydrogen, just saying like, well, they have this spacing because these two values of n have to be integers. This one has to be less than that one, right? Totally ad hoc. Like this is just the way it is. I don't know, right? It started with that. Then, but that was approximate, right? There was approximation there. And then it got a little more accurate because Bohr said like, well, you know, I think we can relate this to angular momentum, and angular momentum has to be quantized. And that's where the quantization in the spectrum comes from. And then in terms of solving the Schrödinger equation instead, now we said like, well, actually, this quantization, there's actually three numbers that are going to come out of these equations all on their own that are quantized. The quantization is just going to emerge from the mathematics, right? And that got us three of the four quantum numbers. And again, not quite exact. And then Dirac, you know, he got spin to also emerge. And it took relativistic effects needed to be included. So basically, you know, I feel like this Dirac quote really does a great job of showing the way the scientific community moves progressively towards more and more accurate descriptions of how things work. I love it. And finally, you know, this was really complicated math to explain the simplest thing in all of chemistry, a single hydrogen atom. And you think, can this be right? Right? That sometimes the temptation is to think like, this solution is so complicated, this can't be right. Right? There's plenty of people, Einstein included, that thought like, this can't be right. Quantum mechanics is too crazy. This can't be how things work. Right? But there's a really great Neil deGrasse Tyson quote that addresses this. It says, the universe is under no obligation to make sense to you. Right? But that's not going to stop the scientific community, right? We're still going to do everything we can to try and make sense of the universe. So congratulations to everyone who stuck through this entire presentation. I really hope it was helpful. So, you know, please subscribe to my channel, check out my website below, and thank you again to Professor Kurt Koloshinsky for writing such a great book, which, again, as I mentioned, I drew from quite a bit for all of the equations, particularly the ones that all had a number associated with them. All right, folks, I'll see you in the next video.